25 weeks left. So you're out of here. No longer here on campus. You're a lifer? All right, so I'm going to write some givens and we'll do a sketch so you have an idea of what's happening. I'm going to do English units. I did post the grades on Blackboard. I didn't know if you knew that. Okay. So we're going to do a little bit more math. Actually, we'll do some differential equation today. And if you ever noticed, the actual, this course is considered a math elective, but it's required in the mechanical. What's that? Have you, we'll have to talk about that off camera.
Smart.
Yeah, I'm gonna.
No, you can't. Okay.
Did I not give you V1?
No, use M1. We don't need that.
Did I? Hold on. Did I use it?
Look at that.
Oh yeah. Thank you. Thank you. I was like confusing me, guys and girls. Yeah. S for seconds. Yep.
The red and blue represent like hot water, or
It's just different. Yeah, right now it's just different. Yep. We could do that, but then it's a little bit of thermal, and I'm not gonna do that. So the dotted line represents the level, water level in the tank. Actually, one line is hot. Yeah, we are doing hot water, but that's fine. Cold water is the 8 feet, so 2 is. Oh yeah, look at that. I actually did that right. 1 is hot. I should do like purple for 3, but that's okay. So we're dumping hot water in, which is 1, and cold water in at 2, and it comes out 3. And we want to actually find the height of the water as a function of time, which we can do that. I'll do that later. But we can also figure out at 10 seconds what the total mass is in there and the total volume or velocity of this water level. Okay, so I'm going to show you the steps how to do that. This actually, I should give this to Mr. G, and this should be in DiffyQ. I don't think everyone's taking DiffyQ, I think, in here. You're in it right now. Okay, that's fine. Have you ever covered this? Did you ever do anything like this? Sort of?
Just a couple, but I didn't study, so
okay.
I don't really learn much from calculus.
Yeah, I
in that class, but that doesn't mean I'm learning anything. Oh, yeah, I just talked to my designer, and she's getting it.
I think the mic.
Where are you taking it from?
I'm casual.
Yeah, okay, that makes sense.
I just show up to
I
class.
was explaining them.
Yeah, I guess it is.
Yeah, right.
So just a few things. If you remember from English units, the density of water is 1.94 slugs per feet cubed, or it's 62.4 pound mass per feet cubed. Does everyone understand the problem? Okay.
Sorry.
Yep. So we're going to find three things: the mass of the tank at 10 seconds, and the velocity of the tank, or the top of the water level. Okay, and then we'll find the height as a function of time, which is your differential equation. So we can put. Why don't we just put find here, and then I can scroll down. A mass of the tank at 10 seconds. See, I think if I would have done brackets, I think that would have helped decipher it with 5 or seconds, right? I don't know why they don't just incorporate that. They should. Yeah.
They're just different
Different units, yep. Just to refresh you. So we're finding the velocity of the top of the water level. And then we'll find, what did I think I call it? H.
mass of
The water level. Yep.
The mass of the water in the tank.
Yes, mass of the tank. Yep, mass of the water in the tank. Yep.
That's including the mass.
No, it's just the mass, I think, of the water. Yes. Yep. Yep. It's all the way to the bottom. So we're pretending it's filled all the way here. So that number 3 is pretty close to the bottom. So I think I can scroll down. Actually, we should do some assumptions. I think you're starting to learn what assumptions are, which is really good. What do you think one of them is? Incompressible, yeah, good call. Is it?
No, just steady flow.
Yeah, we just have steady. It's not steady state because what is something the water level is changing as a function of time.
Oh, I thought what I was wondering was going up.
Yeah, but
Nope.
Well, not equally because we're checking the height.
Because we're checking the height of the water level.
Well, I guess technically we don't know it's not.
Yeah, but we know we're going to assume that it's not. If we find out it is, then that's fine. You're not breaking your assumption because yeah. Okay. But because the water level could change up and down, it's not steady state. If I told you the water level stayed constant, then yes, whatever comes in must equal going out. Let's see. No, it doesn't. Because, okay, the other thing we're going to consider is, and we're going to deal with more of this later, V3 we're going to assume to be constant. Okay. It's not a valid assumption, but for right now, to give an idea, it is. Why isn't this? You remember?
Why does it?
Yeah.
Because the velocity change based on the height of the water.
Yeah. Yeah. So the higher it up, it should be higher, right? Because you have more pressure pushing down. But as it goes lower, it should decrease. Okay. We're going to do another problem that later on, I don't know if it's today or next time, that deals with, we're not going to assume that. We're going to do something else. Slightly different problem, but it's the same concept.
So how are you to know when and when not to assume that it's, or are you always just going to basically assume that it's going to be constant? Unless it states that it's
We haven't covered Bernoulli's right now, but you have in the past. Typically, we could figure out what it is. Typically, you could do it right now because the water level is not wicked high, so that assumption is pretty close. So this number is going to be pretty close. It's still going to change, but that's fine. Question so far? All right, so let's do this. Solution. We're going to start with the conservation of mass. So dm of the system, dt, equals the summation of m dot in minus the summation of m dot out. So the left-hand term, this dm dt, that system is the tank mass. So the rate at which this is changing has to be something to do with what's coming in and going out, right? And you have to write it in differential form because you want to find an instantaneous mass change with respect to time. You don't want to find an average, because this gives you a more appropriate solution. So let's find mass flow rate in. So summation of m dot n equals m dot 1 plus m dot 2. M dot 1 was given, right? Yep. And m dot 2, you remember that equation? Find mass flow rate if you know three things. Rho AV, yep. So let's put it up here. I'm breaking my rule, but that's fine. You get to the point where you've graduated from all that. This is the row of the water, right? At 2. And might as well write it one more time. Because what do we know? We know the diameter, right? So it's rho of the water pi d2 squared over 4 times v2. So we're kind of doing a review in this problem. The reason we're doing this review is because after the test, we're going to get into momentum, which deals with forces in fluid flow, and you need to know mass flow rate and understand all that. Okay, so we're going to use pound mass, because that's the same unit here. So 62.4 pound mass per feet cubed times pi times 0.052 feet squared over 4 times 8 feet per second. Is that big enough in the back, Adam and Adrian and Kirsten? And we get 1.76 pound mass per second. And we'll do the same thing for mass flow rate out. M dot 3, which is rho of the water, A3, V3, pi D3 squared over 4 times V3. .4 pound mass cubed times pi times So we end up getting 1.76 for mass flow rate in and 2.33 pound mass per second going out. So is it steady state? No. So we know that what's actually happening? Flowing out faster, so it's actually decreasing, okay? So, what's that? I don't think it is. No, what did we start with? Yeah, it's actually only going to lose 5 pound mass. Yeah. So, let's review this to show you. We started with this. This is the fundamental equation for conservation of mass. You can use this anytime you ever wanted to. Okay? This is a differential equation. And what we can do is we can find mass flow rates in and out. And in this example, the velocities are always constant coming out, right? If we look at the top, coming in here is constant here, and going out is constant. I could tell you they're functions of time, right? Sure, you just keep them in terms of time, and when we do the next step, your differential equation isn't as easy. So what we're going to end up with is this equals a number, and then we're going to solve it and integrate to actually get what we need. Tyler? Squinted. Question? Oh, okay. You're like, something didn't work out right. Okay. So, now, dm of the system, dt, is equal to 1.76 pound mass per second minus 2.33 pound mass per second. And we can might as well call it mt, which we're looking for, same thing. And that equals negative 0.516 pound mass per second. And the negative makes sense because it's decreasing.
Yeah, I got 5.7.
You got 5.7?
Yeah. That much though? Yeah, that's cool. 6. 0.5, 0.05, I mean.
What? Did I wrong? You both have 0.57?
1.76 minus 2.33. They have 4.57.
All right, sure.
That's
We'll
all
just,
I know.
okay.
I don't know where that's
Okay. Don't ask me how I got that one. Must have been I didn't round at all or something.
Yeah.
So I'm going to rewrite it like this without the units, just because this is something that you've seen before, right? This is a differential equation, right? Yep. And you integrate. So we'll do it 2 ways. And I think it'll be the same thing I showed you guys. And hopefully it'll click for everybody else. Okay, we're going to do it 2 ways. We're going to do option 1, plus C. Okay. So we're going to integrate dm dt. I'm doing this off my hip. I didn't do this one in my notes. So we're going to integrate that. What do we get over here? MT equals, and what about over there? Because you're integrating respect to time, and then we add a constant. Okay, how do we find, now, has everyone seen this? How do we find C? How? What do we know at t equals 0? What's mt? 620? So yes, so 620 equals negative 0.57 times 0 plus C.
Yeah, but how do you know like 0 is 620?
Because I told you that in the givens.
Well, I would have M tank equal.
Yeah, that's what tank 0.
Well, this is M tank. How would I know it's 0?
Mass of the tank.
Yo, Sam, doing that YouTube class, bro.
So the 620 was at time 0.
Okay, fine.
Say that again. Yes, it's the mass of the water in the tank.
Yeah, I got confused about that. I labeled it H2O.
Oh, you mean at the very beginning in the givens?
Yeah, that one was the mass of the tank itself, wasn't it?
Oh, okay. So this, I'll have to fix that, is that, and that is the mass of the water in the tank. Is that okay now?
Yeah.
Okay, let me fix that.
But that's just that time here.
Yep.
So we don't know the mass of
No, but we can find it now, right? Let me fix that. Mass of water in tank. All right, so what is our equation now? Mass of T equals negative 0.57 times T plus 620. Make sense? What is the unit of this one?
Pound mass of a second.
Yep, because times by a second gives you pound mass.
Pound mass.
So let's plug it in, and then we'll do option 2. So mass of the water in the tank at 10 seconds. And what do we get? 614.3. Sure. We'll just round it. 614. Who hasn't taken, I know Jessica hasn't, heat transfer, and you haven't. It's a few of you. Okay, so a majority of you have. This is very similar to what you do in heat transfer. What did we do? We applied these. These are actually initial conditions, right? But in heat transfer, what do you apply? Boundary conditions. You do it the same way at x of 0, whatever value is whatever value, and then you plug in to get your equation. Okay? So, let's do option 2.
What is this one limit?
This is the one of the limits. So
your equation for the mass of the tank times the amount of cycles should just give it. You don't need the C, right? That tells you how much is going out.
sorry, say that again.
So you know how we solved the C there?
Yeah.
You didn't need the C at all because you know that the change in the mass of the tank is negative 0.57 times the 9. So you can just take that and then subtract it from
You could do that too, yes. But we could do it nice and easy here because this is a power of 1.
Right.
When it becomes a power of 2 or more, then you have to be very careful. So option 2 is we're actually going to put our limits on. So dm of the tank from the initial value, which is 620, to some final value equals negative 0.57 dt, and that's from initial time of 0 to a final time of 10. Yes. Yep. I'm just going to leave t for right now. This is a good review too. why, so you, for me, try to remember this, is I always plug in the bottom numbers. Because those are basically the numbers you're going to use to find your constant, which you had over here. The top I keep as variables because you can find an equation. If you kept 10 here, then you get one number. You wouldn't have an equation. Okay? So when I integrate the left side, what do we get? MT, right? Because it's 1 times dt from MT to 620. And then over here, negative 0.57 times t from t to 0. Then we do this. MT minus 620 equals negative 0.57 t. And then minus a negative 0.57 times 0, but that's all 0, right? So you get the same equation, no matter what way you do it. Sometimes one way is easier than the other. It doesn't really matter. Questions so far? Does it make sense? Or getting there. Good. I'm glad light bulbs are going off. Okay. So we found, we'll take a break after we do, probably in 10 minutes, but probably 7, 8 minutes. So let's find the velocity of the water level in the tank. So we know that this is equal to the density of the water in the tank times the area of the tank times the velocity of the water in the tank. Top level. Right? Does that make sense? Because we know the mass flow rate of the water in the tank, which was what? Negative 0.57. So as long as we know that level, that water level is going at that rate, well, we know that rho times A times V is the same, it's like the mass flow rate. So what we're going to do is just going to rearrange, and we're going to solve for VT. Okay, how did I do that? Okay, so I called it m dot of the water level in the tank over rho times the area of the tank. What was the area? 2 feet. So what's the radius? 1 foot. So pi r squared. So you actually end up getting, I'll do it out here. So 2 feet squared over 4, which is really what? Pi, yeah. So anytime you have a diameter 2 feet or 2 meters, it's going to be pi. Yeah.
Why do you use a 0.57 for MT and not like negative 0.57 for 620?
Because you're saying, why didn't we use this one that's boxed in blue?
Yeah.
Because that is mass, but not mass flow rate.
Oh, okay.
Okay? Because mass flow rate is equal to that. And we know mass flow rate is rho AV.
Okay.
So we end up getting negative 2.6 e to the minus 3 feet per second. Not very fast, right?
With the different numbers, 2.9.
Oh, 2.9? Yeah. Okay. So let me fix that.
Oh, yeah, really well.
Okay, so 7 7, 7, 7, 7.
I do.
Good? Last thing, then we'll take a break. We want to find the height as a function of time now. No. Okay. So let's find h as a function of t. So I'm going to start with this again. So we've actually manipulated this equation a few times. There's another way you can do this. It's kind of cool. There's so many different ways you can do and look at a problem. Can someone tell me, how would you find the mass of the water in the tank? You know the height. You need the area. So say at one time, if we knew the density and what else? You're on the right path. And the volume, right? Because that's a fundamental. So we can break up volume in terms of H. So rho A of the tank times H. Huh? Okay, sure. Nice.
The rho V is mass flow rate too, right?
Rho AV is mass flow rate. So what I just did there was I found the mass of the water in the tank at one specific time. And what we're going to do is we're going to plug that here. Rho ATH over dt equals negative 0.57. Have you ever seen this? Anybody ever seen it like this? Just broke it up, plugged it in. Yep. No? It's pretty cool, right? I think it's pretty cool. Now, what can we do here? Is rho constant? Yeah. So we can take that out. Is A constant? We take that out. Is A? No, we leave that in. So we end up getting dH dt equals negative 0.57. Not yet. I'm going to take out rho and AT because they're constant. I'm going to divide by them. So you can take rho and AT out and then divide by them. And holy smokes, look. What is this? It's another differential equation that has H. Like all this is constant over here, right? So you can just integrate it like we did with the mass, and we end up getting this for an equation. Times T all over rho times the area of the tank. Now, is this what I'm going to have you do on the homework? I think it might be... No. Okay. So we're going to do another problem on Thursday that deals with very similar, but we're not going to assume V3 is constant. We're going to assume it's something different. Okay? Yes?
Isn't mass flow rate rho times volume?
Yeah.
Yep.
So how do you break down volume? So area, isn't it the area times velocity?
Yep.
So how do you use rho a h?
Yeah, you're missing.
No, that's mass. It's just mass.
Yeah, no,
It's not mass flow rate. It's just mass.
I know it's not mass flow rate, but like, isn't that what's supposed all mass like empty?
It's in the parentheses.
There it is.
Yeah.
That was
Yeah. We manipulated this. No, not that one.
It's a morning, man.
Oh, we manipulated this one how many times? Kind of like 3 times, right? The first time was to find what? The number. The second time was to find the velocity of the level, and then the third time was to find h.
Because you
Doesn't matter.
You use a dots before, like on top of the answer.
Yep. So like, I could call this just m dot t. Oh, it does, right? Okay, so let's take a 5. Let's start at 25. I'm gonna show you. We're gonna review Bernoulli's in a pitot tube, and then we don't have time to do that one. Oh, maybe we'll do that, and then I'm gonna let you go after that. So 25. So take like 5 to 6 minute break. Five, 6 minute nap. What?
Shit, where do I get one of those?
Okay, so let's kind of review pitot tube and Bernoulli's. So say we have a streamline and we pick 2 points on the same streamline. What do we typically do from one point to the other? Remember? We talk about Bernoulli's.
Write the equation and see what we
Yeah. So what is conserved? Energy. So what energy? What does it have at state 1? Okay, that's the easy one, right? What else? You said potential. Flow work. Yep. Yep. And what else? If you've taken thermo. Internal, yes. And that's the same at state 2, right? But stuff could change. Plus P2 over rho. If you remember from thermal, this is really the conservation of energy. Over here, there was system energy, right? On the left. Oops, sorry, I'll wait till you finish copying that. So over here is system energy. Okay? For example, if you have a car going up a ramp, the car is traveling up. So over here, you could have kinetic potential, right? And the car could change. So that's your system. But if we are looking at this room, on the left side, is there a change in internal energy if we say the temperature is constant? No. Is the room moving? No. So there's no kinetic. And are we changing this whole elevation? No. So that's what that is. Over here on the right is stuff going through the boundaries. So the Bernoulli's equation, which is this black one, is actually part of this, the fluid energy. Okay? So when we deal with Bernoulli's, what typically do we neglect? Temperature differences. Okay? So these equations actually come from this right here. All right, so you start with the red one. You can bring in everything because there's no work, there's no heat, and it's steady state. So we just have this. Okay? So this is basically, let's rewrite it in blue here, P1 over rho plus V1 squared over 2 plus rho Z1 equals P2 over rho plus V2 squared over 2 plus rho Z2. Yeah.
Is there just another way of writing that where it incorporates G?
Yeah, did I miss G? Times by G. Oh, it should be GZ. Yeah. That's G. Good catch. Yep. Yep. Well, I don't know why I wrote rho. No idea why I did that. G, there's anything else? No. There is a different, and I was going to show you that too. So you could write it like this.
Oh, okay.
Doesn't matter, right? Because you can manipulate them all. They just have different units. Like this one would be units of feet or meters, right? This is typically what you see when we deal with pumps. Typically, an energy for fluid, usually you kind of write it like that if you're looking at that. So let's look at a pitot tube. It's P-I-T-O-T. Sometimes you see pitot tube or pitot-static tube. You remember what they're used for? Yeah, airspeed, yep. So we can actually use the Bernoulli, and I'm going to show you that, to find how to figure out what the velocity is. So you can have a pitot tube in your car if you wanted to calibrate it. Sure. There's two ports, right at the front, and then there's static holes all the way around on the side, which is point 2. There's many holes. I think there's 4 or 5 different ones depending on the size. And the blue one goes to one side of a manometer, and the red one goes to the other one. So you can measure a delta P. So let's write the Bernoulli's out, and we'll do it in this form. Does anybody know why these holes right here have to be this like far enough back?
Well, one's the stagnation.
So let's, yeah, one is the stagnation. So let's look at this. As the flow comes in here, it has to do what? Go around and go, like kind of turn and then kind of eventually level out? Okay, that's what we're looking for. We're looking for it to be like kind of straight now. We don't want it to be at a curve because when it's at a curve, it actually increases the speed. So it has to be far enough back. Okay? So what happens is this hole is pretty small. As the air comes in, it slows right down. So we assume the velocity here is 0. But this part we have velocity going over, so we have some velocity. That's actually the velocity way upstream. Elevation changes. Yeah, there is a slight elevation change, but we neglect it. So we get rid of these and that one. And we can rearrange to get this. 2 times is it P1 minus P2? Yeah. Because P1 has to be higher. Over rho.
So what do you rid of the velocity?
G's cancel, right?
The first part?
Yep, I'll tell you. Over rho of the air. Because what happens is this hole's so small that it comes right down, slows right down pretty much to 0. We kind of assume it's 0. Even though there is a little bit, right? But we just neglect that small change. Yep. So the velocity at 1 is 0, the elevation changes are neglected, and we can rearrange and actually solve for the velocity, which is really upstream, which is really good. Now in this, the density is the density of the air. Okay? So we're assuming that it's low speeds, meaning the density doesn't change. High speeds, it's a little trickier. If the red and the blue were hooked to a manometer that used like mercury or water, then to find delta P, you have to use that density. Because there's going to be a homework problem that's going to have you to do that. Practice. Like say these two were hooked to a mercury manometer, you have to use the density of the mercury to find the change in pressure. Okay. How did they do that? Yeah, that's fine. You'll see on the question, and hopefully it'll click. All right, so on Thursday, I don't want to do this other problem because it's a little long. I don't know if I want to do that one or a different one. Let's see. On Thursday, we will do a very similar problem that we did today, but we're not going to assume velocity to be constant at the outlet. And you're going to use that, and you're going to actually plot that as a homework problem in MATLAB using a numerical method that I'll show you. Okay? No, you start with your initial value and you mark forward in time. I'll show you how to do that. So I will post the homework sometime today so you can start working on it. Kind of like a review. Then we'll continue stuff Thursday, and we'll talk about non-dimensional numbers on Thursday too. Okay. Make sure you see me about your homework and